Good afternoon, ladies and gentlemen. We're from St. Paul's Co-Educational College of Hong Kong. I'm Yuki, this is Angel, this is Justin, and Kinsey. So today we're here to talk about the human carrying capacity of the Earth, and we're going to talk about some crucial factors affecting the carrying capacity and how we got it to be 4.09 billion, and also proposing some suggestions to increase it.
So carrying capacity is defined as the maximum population an environment can sustain indefinitely, and it is affected by four factors: the rates of consumption and production of resources, as well as the current rates of damage and recovery of the environment. And we have mainly 5 assumptions. The first being the current conditions and technology do not change, as they would directly affect the rate of production of resources. And secondly, the consumption of resources and carbon emissions are linearly related to the population, as shown in the graphs. And the third assumption is that the effect of economy and society by the increase in population are not taken into consideration, as social breakdowns would happen before the carrying capacity is reached. And fourthly, astronomical time spans are not taken into consideration. And last but not least, all the planet's accessible resources will be used to support a hypothetical maximum population. And we'll have the crucial factors divided into 2 categories: resources and the environmental damage. The first category, resources. And we've thought of space, energy, food, and water. We considered food and water because they are directly related to our biological needs and they are relatively scarce. While for space, it is of relative abundance, as in we have enough space for people to live in. And for energy, we are not taking it into consideration because it will be arbitrarily large, given that we are technologically and economically possible to introduce more usage of renewable energy sources. For damage and recovery of the planet, we've considered carbon emissions because from our sources, the planet's atmospheric carbon emissions should be kept. Concentration in the air should be kept below 450 ppm to avoid long-term environmental damage. While for the damage of the nitrogen and phosphorus cycles, they are having less pronounced effects and can be solved in similar ways as carbon cycles.
So next we're going to talk about our formula for the model, and here we basically extrapolated the current conditions to future conditions based on how many resources were available and how much were consumed. So these are the formulas for food and water, which you can see basically follows the same basic pattern, and these are the ones for carbon emissions. So what we did is we collected data from these sources, which we found to be rather reliable, and therefore used these to find out what the carrying capacity was based on our formulas. So what we did was we calculated the maximum population each of these factors could support individually, and then found the smallest number, which would be the limiting factor that affected the maximum population. And finally, we found that carbon emissions were the limiting factor, and that our planet could support 4.09 billion people based on this calculation. So we basically divided the problem into 2 parts. So the first one was a realistic scenario where there was waste of resources due to various reasons, and the second one was a more idealistic scenario due to basically assume that there was no waste in this ideal scenario. So what happened was that we calculated both the realistic and ideal scenarios, and for the ideal one, we assumed waste to be not present by adding it back to the supply of resources. And because we couldn't find any data regarding unnecessary carbon emissions, and that it was difficult to quantify whether carbon emissions were unnecessary, we did not change the carrying capacity of carbon emissions based on this. So finally, our conclusion for the ideal scenario was that, again, our planet's maximum population is capped at 4.09 billion based on carbon emissions.
So here are some strengths of our model. Firstly, our model is robust to change because only the factors affecting the carbon emissions will affect the final result. And the second strength would be our comprehensiveness because we divided our model into both the ideal and realistic situations. And for the third part, our model is rather computationally simple. You see, we only use a multiplication and division, so it's very convenient and rather efficient. So here are some weaknesses of our model. Firstly, it can be considered as inaccurate because our whole model and our whole result is based on the assumption that the population is linearly related to the consumption of resources and the carbon emissions. And our second limiting factor would be the limited consideration of factors, which include some, like, for example, human factors, and because we cannot quantify or estimate how these factors will come into play into the carrying capacity. Yes, so anticipating future conditions, we expect an increased consumption because of the rising living standard and quality. So yes. Okay, so here we see a photographs of the carrying capacity and the population. So, as mentioned, carbon emissions is the primary limiting factor for our planet's carrying capacity. However, when even operating above carrying capacity, carbon emissions will take a long time to build up, so their impacts will be less pronounced. The slow-acting nature of global warming and carbon emissions will also mean it will take a very long time for the carbon emissions in the atmosphere to be absorbed, which means the temperature will take a long time for the carbon in the atmosphere. The temperature will continue to rise even when the population starts to drop. And therefore, we think that scenarios C and D, both are overshooting, are most likely, with situation D being the more likely situation. So this is because of the delayed reaction of the damage done by the carbon emissions. Moreover, the increase in carbon emissions may also possibly heat up the planet to a point of no return where there's irreversible ecological damage. Okay, with that being said, scenario D is entirely possible because where humanity is entirely wiped out before the carbon levels return to normal and the Earth starts to cool down. And our predictions did not account for human behavior, which is a significant factor. When we account for human behavior, we can expect that when food and water are scarce, people will start to conserve resources. And as more and more research points to the looming threat of global warming, hopefully more efforts will be made towards reducing carbon emissions.
So now I'll talk about the solutions to increase the carrying capacity. So first, for carbon dioxide, we have to reduce emission first, so we can use renewable energy such as nuclear and wind power, and in this way we can theoretically reduce emissions to zero. But even if this case, the carbon dioxide level in the atmosphere still takes 99 more years to return to equilibrium, so we suggest to use some additional methods to increase absorption of carbon dioxide, such as afforestation, and also other methods such as turning the carbon dioxide into rocks and also stripping oxygen ions from carbon dioxide so that we can remove them from the atmosphere. And just to add that we did not choose afforestation as a major measure because each tree can only absorb 48 pounds of carbon dioxide per year, and we have to plant 400 billion trees to compensate for the emission rate now. As for water, also a very important thing is to reduce the demand, that is to reduce the waste and water consumption. So 69% of used water is wasted every year, and we can improve this by using more efficient irrigation systems, as 50% of agricultural water is wasted. So some examples of the irrigation can be deficit irrigation, where we just put the right amount that the plant need for the crops so that no water will be wasted, and also drip irrigation, where the water are administered drop by drop to the crops so that to minimize the water loss. And Also, we can see that 900 billion gallons of domestic water is wasted due to some leaking faucets. So we have to increase people's awareness on this issue so that we can tackle this problem by roots where there is too much waste. And also we can try to increase the supply by building desalination plants and also mining glaciers and ice caps. But the later one is not as preferred because it's not really sustainable, and also it may cause some irreversible environmental consequences. So as for food, again, we have to reduce the waste by means of education, advertising, and also levies. And at the same time, we can increase the supply of food by cultivating more land, as only 36% of arable land is used right now. And also we can try to counter land degradation, as 20% of land used now is experiencing degradation. And also we can try to develop more GM food, although it might be very controversial, but a study shows that the GM crops can increase the yield by 22% on average. So this can also be considered. So in conclusion, we got the carrying capacity to be 4.09 billion. And although carrying capacity is just an estimate, it does give us a glimpse into how much we have to do to support ourselves so that the Earth can still sustain humans. So as we have already exceeded the carrying capacity we have calculated, so it's time for us to expand the carrying capacity by improving the technology, reducing waste, and also reducing carbon emissions. Yes, thank you.